So welcome you all for the session on NumPy. I think I need to have one more at least because it's a huge thing to cover. But today what we will concentrate is on broadcasting feature of NumPy. Now what we are going to do is today we have some n-dimensional array. Okay, we'll call it as ND array, and then we want to do some operation. It could be plus or maybe multiplication or division, whatever it could be. And then there is another array. Okay, there's also an n dimensional array. Now let me call this as A and this as a B. Any operation. Okay, let me call this as an operation. Now when you want to do some operation on an array, always if I say A, you can assume that it's some n dimensional array. It can be anything. We are not restricting on what type of dimensions they are going to have. And then this also another matrix which could be of any dimension. Now I want to perform an operation here. Now easiest thing to perform this operation, let me tell you, if the dimensions are exactly same as each one. Okay, A and B, the dimensions are exactly same. In the sense, shape of, you know that shape is a tuple giving the dimensions of different direction. Suppose 3 by 3 by 3 is a cube. Okay, so if shape of both A and B are exactly same, then I can perform the arithmetic without any issue, because if I am doing a plus, I will take one element here, the exact corresponding element here I will add, and then I will get the result which is also in the same shape as the original A and B, which will be 3 by 3 by 3 in this case. So if I have to do a plus operation, I will perform element by element. I will pick this element and this element, I will perform that operation and keep it here. Similarly, I can do that on all the elements of the array. Now this is fine. This is the easiest thing to do when the shapes are equal. It doesn't matter if it has to be a square matrix. It could be anything. Okay, it could be anything like this. But as long as the shape is same, I can perform the operation on between these two matrices. I'm not talking about matrix multiplication here, element by element operation. Okay, element wise operation. I'm not talking about any transpose or determinant or whatever. Those matrix operation I'm not talking about. It's a element wise operation between two matrices. I can perform it if the shapes of the matrices are exactly same. Now what if I don't get the exact shape? Suppose I have a, maybe take an example of 3 by 3 matrix, and then I want to multiply it by a scalar value, which is a single number. Now how do I make this NumPy library to behave the same way that it would take if it is of a same shape? It should take it, but it's not that arbitrarily it will accept whatever you give, but it has some built-in rules which will be applied when the shapes of the matrices are not exactly same. When I say not exactly same, it means that 3 by 1 by 2 is not same as, its shape is not same as 1 by 3 by 2. Okay, though the number of elements are same, they are not same in terms of the shape exactly, because 3 comma 1 comma 2 is not same as 1 comma 3 comma 2. All the values should be in the same way. It should be same. It should be, if you want to call it as a same, but still there are some rules that you can apply on finding the dimensions of the matrices which are involved in the operation to say whether it is possible to perform the operation. If it is so, what is that it is going to do given the matrices which are of different shape, and what will be the result that you may get when these two matrices are operated upon. That is the focus of today's discussion, which is called broadcasting. Now before I go into that, I want to just give you some example of a real life matrix, which is a good example is an image, and then few dimensional 1D, 2D, 3D, we'll see it on NumPy, and then we'll get into the broadcasting feature of NumPy. Okay. Now, I am not yet told what is broadcasting, but assume the intent is to perform operation element wise between two matrices of different shapes. Okay. That is a one summary of what the broadcasting is meant for. Now let us take an example. Image pixel. I have told many times what is an image. As I told you earlier, an image is nothing but a set of pixels arranged between in a row and column. Now let me call this as a origin, and this is the x-axis 0, 1, 2, 3. I'm sorry. This is yeah, that's okay. Now this is another. Okay, I will not call it as axis x axis. Axis 0, axis 1. Okay. Now this is going down with this row wise, and then column elements are given as axis 1, and it is given as origin is here. Now what are those individual pixels have? The individual pixels are going to have the intensity of RGB, the basic colors. I am always assuming a luminance is something different, but we'll just worry about only the RGB values, so that the combination of these colors give you a particular color in a pixel. So what is the range of colors you can have? It depends on how many bits you reserve for particular R in a pixel. Suppose we reserve only 8-bit for this, then what is the range of colors that you can have? Don't say 2 power 8, it is 2 power 24, because this will take 2 power 8 values, this will take another 2 power 8 and 2 power 8 values. So multiplication of this will give you the total amount of color palette that you can have on the particular pixel. Once you can choose a color on a particular pixel, then you can choose the remaining pixels to display a image. Now when I have 3 colors, and individually these colors have to have an intensity value. If suppose all zeros means there is no red color at all ones, 8 ones means it's a bright red color. In between is a shades of different shades of red color. So that's similarly I can have shades of this, shades of B, and then combine all of them. I can have reproduce so many colors on the screen on every pixel level. Now number of pixels that you can keep gives you the resolution of the image. Suppose HD image is some 4K image, they say 8K image, whatever. It shows how many number of pixels are there in a particular area. So that shows you the resolution or the quality of the image that you have. And individual colors that decided based on the number of bits you reserve for the basic colors RGB. So this is the background of that. I have many times I have explained this. So let me now explain. You want to keep all the color values, red color values for every pixel in the image. So every pixel will have all 3 components. So combined effect is what you are seeing on the screen. So this and this and this all fall under one particular area in the image, which is 8 by 8. So a combination of what you have here is the combination of RGB colors that you have chosen. Now suppose if you have chosen all of them 0, you will get a black dot here. If you chose all of them high value, because we are assuming it is be a 8-bit number, if you say all of them are FF, you will get white here. Okay, this spot will be white. So now you can imagine this space in my image. What will be the combination of RGB here? Because this is okay. As I draw it, it becomes red. But this white area is a combination of RGB. So if you want to store these values, you need to have an array of 8 by 8. Okay, because number of pixels are 8 by 8, and then into 3, because I need for 3 colors. And individually for each color, I need to decide whether I want to store it as a byte or a word, whatever. Now this is the screen, how it is displayed. This is X and this is Y. For our NumPy case, we will call this as axis 0 and axis 1, that we will see later. Now this is the image, okay, 8 by 8. Now you can see that these pixels are having only the red values, which is FF, and green and blue are zeros. That's why you see a red here. Whereas this is pale green, so it will have a combination of two colors, and yellow is a combination of red and green. So maybe if you keep both of them high, you will get a yellow. FF, red and green are FF, then and green, blue is 0, you will get yellow here. So this is how the display is drawn. Now how do we, now we are not bothered about knowing the graphics, but we are interested in knowing how do you access each of the pixels. So origin, I said it is 0 0 here, then I mentioned that this is the x-axis, so this will be 7 0, okay, 0 1 2 3 4 5 6 7, so 7 0. So we are taking one point here, and then we are writing the x and y coordinates, okay. So do not assume that this is 0 and this point is 1 2 3, then it will be 8 comma 0, okay. You might get confused, but what I am trying to find out is the coordinate of a particular pixel, okay. So there are 8 pixels are there, and my indices are say going from 0 to that value. So 8 by 8 will have index varying from 0 to 7. Then it's very obvious that these are the values, 0 comma 7 here and 7 comma 7 here, okay. It's not 8 comma 8. Okay, now this you understood. Now let us see some general rules of what is broadcasting. I level I told you what it is, but we will see now. Two dimensions are compatible when they are equal or one of them is 1 or a scalar. Now the broadcasting feature, I mentioned that it is for multiplying something, or not even multiplying, performing some operation element by element. Now I will say that the matrix A and B are compatible if they are of same size, okay. Both are of 2 comma 3 comma 1 and 2 comma 3 comma 1. Yes, it is compatible. I can perform this operation, be element wise, done. And if it is scalar, okay, some operation I want to do, but if it is a scalar, some, let me call it as S1, then also it is compatible. Then what I will do, I will take this value, I will perform this operation on all the elements that I have. All the elements I have, it doesn't matter what is the value I have, okay, n and m and x, whatever, it doesn't matter. I perform the scalar, I will take one scalar and perform the same scalar operation, okay, whatever operation I mention, plus means I will add that scalar to all the pixels or all the data element, or I will multiply or divide, whatever. So if it is a scalar also, no issues, okay. I don't need any major things to do, okay. I don't have to validate it because it is straightforward, I can apply that, okay. So that is what I mean by broadcasting general rules, okay, first one. Now what is the second? When the dimensions are not compatible, in the sense they are not falling under one of these categories, they are not of same shape, they are, one of them is not 1. So 1 means it's a scalar value, remember that. So if I say, if I multiply, I have a matrix like this, and then I say 1, this is a scalar value, okay, it's not a one dimensional array or something, only single value is there, then it's fine, okay. Now what if I have something different? Then NumPy compares their shapes element wise, okay, it is performing something element wise, it is comparing, and starts with the trailing dimensions and works its way forward. So trailing dimension means, suppose if I have 5 by 3 by 2, trailing dimension is this. So it is going to go from here to here and then start doing something, okay, I have not told you what it is, to see whether I have a compatible matrix or not. Suppose I have some x comma y comma z, these are the dimension, it may be all of them may be there or may not be there, but it will start comparing, given one A and given another B, it will start comparing this first and then this and this, it will go on comparing and trying to find out whether these two matrices are compatible for me to perform the operation that user want me to do. So this is the trailing number, and then it will start doing it like this way. Just believe this is what it's doing, but you will understand what I mean by that. Now this is the 8 by 8 matrix which I mentioned. Now if I am having a scalar value of S1, okay, let me show this. Now image 3D array 8 by 8 by 3 x comma y comma RGB. Now what I mean by RGB here is this 3 means RGB. Now when this array is 8 by 8 by 3, it is one particular square. Okay, this one square. It is 8 are there, 8 are here. And then when I say 3 of them, I will reproduce this thrice. So one here, one here, one there. So the 3 is applied on this. Okay, when you are having multiple dimensions, you have to assume writing, coming from the right side, the 3 is there. First you encounter 3 here. That 3 is applied on this 8 by 8. That means there are 8 by 8 matrix which are of number 3. 3 times are there. Now suppose if I have 4 here, it will be 4 times the 8 by 8. And then you come inside and then see that, okay, this is only 2 of them are there. 2D is very easy for you to imagine. So 8 by 8 you can imagine. Okay, this is how you have to read a multi-dimensional array, how it is given. I just expanded the 3 for RGB values. Okay, now I want to scale it by another scaling matrix, a one-dimensional array which are having 3 values. That means what? I am applying a scaling S1 on all the red pixels. I am applying a scaling. Scaling means what? Maybe if suppose I have a value of 50 in a particular pixel, okay, in the R plane, then what I want to do is I want to apply S1 on top of this. Maybe I will multiply or add or whatever. I want to do some scaling. So let me multiply it. So I will want to multiply this S1 by this value. Suppose S1 is some 0.5. I will reduce it to 25. That's all. So this is what I want to do it on all the pixels that are there in the red plane. Whereas on the green plane, I want to apply a different scaling, which is S2 on all the pixels. Okay, this is what I am doing. Whether this operation is successful or not as per the broadcasting rule, believe it, take it from me, yes, it is acceptable. What does it do? It takes S1 value, apply it on this, S2 value it applies, and S3 value it applies. Now what I am saying is, if you give a matrix of this shape and then you say I want to do S1 comma S2 comma S3 on it, what it will do if 8 by 8 by 3 is there, it will take this one 8 by 8, apply S1 on it, and then it will automatically do by itself. So you are anyway giving only one scalar matrix, 1D array, but it is actually performing in a different way internally. That I will show you the example and you will understand it. Okay, and the resultant matrix what you get will be still the same, 8 by 8 by 3 only, and the individual values are modified now based on this one-dimensional value that you are given. That is called a color scaling value. Okay, now when this is a scalar value, okay, it's not a scalar value, it is it's a one-dimensional array actually. Okay, it is not same as scalar value. It's a scalar array, 1D array. Okay, it's not a single value. If it was a single value, it would have applied all of them the same thing. Okay, if it was just number x, if suppose the scaling was a scalar value, if it was number x, it would have applied the scaling on all of them equally. Same x would have been applied. But here it is not a scalar value. We are doing a color scaling. That means individual colors are scaled differently with 3 values, which is a one-dimensional array. So it is not same as a scalar value. Okay, please remember. Though it is a scaling, do not get confused. Okay, now it accepts even if you have a one-dimensional array of value 3. Whether can I give a 2 here or 5 here, we will see. Okay, now in other words, now what is it doing? It is doing something. Either the dimensions compared is 1, the other is used. Now, okay, when either of the dimensions, when you have 2 dimensions, you are trying to perform an operation of between these two, and if you are encountering a 3 and 3 here, it will take the same value, it will take the same thing. Here it is assuming that there is nothing here actually, but it will assume 1 here, and then it will apply the same thing, it will come back. Okay, it will bring the same dimensions or whatever is there, the same elements, it will bring it back here. Okay, in the resultant value also. I will explain it with the example, don't worry. Now what is happening is, even though you are giving a single dimensional array, it is making you to allowing you to perform an operation on another n dimensional array. Okay, fine. That you just assume that basic things are explained there, but I will give you more clarity on what I mean by this broadcasting feature. Okay, now let us first try to understand some of the NumPy arrays. Now suppose if I have a one dimensional array, I will call it as this as an axis 0, and I am naming it as A1, and 4 elements are there. Now A1 of 1, you are sure you know that it is A, and then E. Okay, that place is misplaced, I will manage it. I don't know why it is so. Okay, I don't like it. Okay, I'll forget. Fine. Now this you understand. Now what is shape of this A1? It is a tuple with a first dimension only mentioned. Okay, there is no other dimension. So how many elements are there in the one dimension? 4 are there. So 4 comma. It is not just a 4 in parenthesis. It is 4 comma in parenthesis to tell you that it is a tuple with single value. Now what about two dimensional array? This is axis 0 and this is axis 1, and origin is there, similar to our image where x and y were there, and we have origin there. Okay, now it's a A2 two dimensional array and 2 rows and 3 column. I am sure you are knowing. So A1 of 0 is E, A1 of 0, so this is the value, and then we have A of 0 and 2 is C, and the shape is 2 comma 3. Okay, it's always a row is given first, dimension is a row major because underneath is C. That's why these arrays are also arranged as row major. So 2 comma 3 is the value. Now what about the 3 dimensional array? 4 comma 4 here, 3 here, and 2 are there in the z axis. So we are calling it 0 1 axis 2, origin is there. Now what about 0 comma 0, this element? Okay, where is it? This element is 0 is here, 1, this x is 1, 1 is here, and z is 1, that is here. Okay, so you are getting that value. Now I'm sure other things you can find out. 3 comma 2, 3 is this one, this row, this value whatever. 2 is on axis 1, 0 1 2, this one. Okay, they are hitting here, and then you have to go on whether this or this you need to choose. That will be based on 0. So 0 is here, so E. Okay, now shape of this is again given as axis 0 elements, number of elements on axis 0 and axis 1 and axis 2. So it is 4 comma 3 comma 2. Okay, fine. Now 3D array you can imagine very easily. Now is this element A3 1 of 1 is visible or not? Now where is it 1? Axis 0 1 is here, this one, and 2's axis 1 is here, and then axis 2 is also 1. That means the element which is below this or adjacent to E below this element, which is not seen here. You cannot assume that the same value is under the cube. It's not a cube, but it's a shape that you cannot assume, so it is not visible. Okay, now how many elements in this A3? In this A3, how many are not visible? You can see this slice is visible, this slice is visible, this slice partially visible, something all of them is here on this side is visible. What is not visible is even this top one is visible. So the innermost of this one, innermost of this behind it, how many are there? There are, even this innermost is also not visible. Okay, only this side is visible. You don't know the other side. So all this thing, other side of this 3 by 2 is not visible. Okay. So 6 elements are not visible. I'm sure you can understand it. Fine. Now, what if I want to write a 4-dimensional array? As I mentioned, you have to come from this side. So when I saw this A4 4 by 3, twice if I have, means that slice what I had, that slice 4 here and 2 were there. This slice, okay, one slice was there. Okay. Now this slice, if I keep one more, then I get a this. Okay, this one. Okay, I get one more of this. I just replicate it. Okay, that is what I do when we have this dimension. Now when I have 1 3 here, the whole thing I need to replicate one more twice. Then I will have this 3 times coming. Okay, that is how this will look like. This 4D array will look like. This is how it is going to look like. Now where is this fourth axis? Axis 0 1 2 we can see. Where is the axis 3? Axis 3 is, it is something like this. Axis 3 is 0 of the elements will be all this, 1 is here and 2 is here. Okay, that is how you will keep on expanding the number of dimensions. I hope this is clear to you. Now can you find out this value? Now when you are 0, that means you are here. You are interested in knowing some element here. In our case, it doesn't matter whatever is the value here, because I have just copied the same thing here, so it will be same. Okay, irrespective of whatever is the value that I choose here, I am going to see the same value because I have just replicated the same image on top of all of them. Now where is this 1 1? It is the same as what we did earlier, so it is very easy. I don't need to go through that, so you can find out. Now A4 is shape is 4 in this axis, 3 in this axis, 2 in this axis and 3 in the axis 3. So 4 3 comma 2. Okay, this is the shape. Now note here that the same contents of A3 is replicated while constructing A4. So A4 I have constructed using A3. So now what happens when a new dimension is added to the existing one? Whenever, suppose if I add one more dimension here, what exactly will happen? Suppose if I have to tell you, if I add one more, what will happen? The whole thing is going to be taken and replicated one more. That's all. So that is how the expansion happens. So which means that the A3 replicated 3 times by adding another dimension of 3 to it. Okay, A3 to A4 transition happened this way. A4 to A5 will also happen similar to that. Okay, I hope this is clear to you. Now matrix operation on A4. Let us see here. Suppose if I do A4 into 5, what do? I do a 5 on all the elements, whatever is there. I multiply it by 5. Every element in A4 is multiplied with the scalar value 5. Fine, no problem. What if I want to do this operation? A4 plus B of 3. Now, because I explained about the image, you might have guessed it now. If I have to perform this addition using a 3-dimensional, not 3-dimensional, 1-dimensional array, but 3 values, bx, by, bz, I want to add that to A4. This is the matrix I have, A4, the whole thing. I want to add a b of 3. Okay. Now, what will happen? You might have guessed it now. All the elements here, okay, all the elements here, don't worry about A, B, C, D sitting here. It could be ASCII value of A, which I can multiply. Doesn't matter, okay, for a demonstration purpose. So, all the values here are going to be added by Bx, okay. All the elements here, including the, which is not seen here, okay, we are not, don't think that what we are don't see is not going to be affected. It is going to be affected. It will be added by By. And all the elements here will be added by Bz. That is what this is going to do based on what I explained to you about the broadcasting rule. So all the elements at 0, that is B4, the axis 3 is 0, on axis 3 are added with Bx and comma at 1 with B5, By. Here all of them are going to be added with by and bz, so on. Okay. Now let me ask a question. If I have a matrix C of 2, that means I have only two values, Cx and Cy. I want to add a, this matrix to the A4. Is it possible to do? You may think that, okay, why not I do not two I'll take and then do it. Okay, it's not going to be performing that way. Now it is going to take, when you give this, it is going to order it 4 3 2 3. This is what is the A4. Okay, now C is a matrix, C is just a 2, so it is going to keep 2 here, and then it is going to perform, the rule is like it is going to perform it like this. Okay, from the trailing dimension is 3, so it is going to compare the dimensions of two matrices A4 and C from the trailing dimension. Now if it is same, it is fine, dimensions are same, the number of elements are same, it is going to be okay. Same number is okay. If one of them is 1, that means one of them is a scalar value, that is also fine. But now I don't have both of them. I am having one as a 3, other one is 2 elements are there. Now is it allowed? Can I allow this multiplication to happen? If I allow, how will I perform the job? Okay, it's not a multiplication, it's addition. How will I perform this addition? Because I have only two values. Now earlier bx, by, bz, I could do all bz, bx I do here, by I do here, bz I do. It's a very easy, and there is no confusion in performing the job. But if I have only two values, what can I assume? Whether the user wants to do cx here, cy here, and then he doesn't want to do anything at all here, can I assume? In that case, the user should have given me 1. Then I would have not touched this value at all. Okay, or 0, sorry. If I am performing addition, I should have got a 0. If I am performing a multiplication, I should have got a value of 1 to make this particular thing unaffected. So the user's intent is not this. So and I cannot perform different operations, because what I need to assume here depends on what I am performing here. So this confusion is there. So unless the user gives me the same dimension or a scalar value which is unambiguous, I can perform the job. Otherwise, the NumPy library will have a confusion to do. It will get confused. So the best option is to reject such an operation. So if you try to do this operation, the broadcasting means nothing but, even though the value is not given, you are assuming that the value is there for everything. See, in our case, only bx, by, bz was given, but I assume that the bx is there for all of them. I applied that scaling for all the matrices, though the user did not give me a exact same size of matrix. Okay, if it was a normal element wise matrix, the user should have given me the same quantity, the same number of element, with all these elements are bx, all these elements are by, and all of them are bz. You should have given. Then it was a element by element operation I could have done easily. But I am allowing some optimization that user, if it intent is to do the same operation, you don't need to give me all the thing. You give me one, I will manage it with that. That is optimization, because memory is saved, and then lot of performance also improved, because you are giving only one value and then asking me to do the operation. So this is what is happening. Now if I give a dimension which is like this, it's a confusing thing. So the NumPy will not accept it. So it is not possible. Only if this value is a scalar or the same dimension as that of the trailing dimension, which is 3 now. The trailing dimension is this one. Okay. If this is also 2, suppose, because I am giving this, if it was 2, if it was not this much, in that case this is not there. Okay, only I had only this 2 element, and then I am giving you cx and cy. No problem, I will do cx here and cy here, and my job is done. I would have accepted it if it was only 4, 3, 2, 2. But if it is 3 now, so I need one more thing. Okay, you cannot give me 2. Either give me 1 or give me 3. Then I can perform the job. Otherwise, it will not take it. Okay, this is what is the broadcasting rule. Okay, to verify whether any operation on an n-dimensional matrix can be performed or not needs to be done from the trailing end. So now you understand that if I need to verify whether a given matrix is proper or not, I need to do it from trailing end, because then only I can keep finding out how many are needed and how many are given. Then I can say that it's not possible. Okay, so this is how it has to be done. Before I go into the thing, let me see whether is there, you guys are, where are you? Okay, very good. So what is that? If a of 3 of 2 of 0 must be g, I think. No, actually you cannot have a 0 here. Okay, 0 element means nothing. Oh, sorry. A3 to 0. Oh, okay, you are accessing a particular element, is it? 1 second. Okay, did I make a mistake? A of 3 of 2 of 0. This one you are starting. Okay, 3, A of 3. Okay, this one.
Previous slide, sir.
Oh, previous slide. Okay, this one. 3 here, 2 there, and then 0. This is 0, no? Where is G coming? Okay, let me put
So
it.
all the face of the G must be Gina, so that's why.
Okay, now why is it so? Okay, let me first of all write 3 is what? Axis 0, 3, this row. Okay, 2 is what? This is 0, 1, 2. So this column, it should be something which is interfering with this. Either I should have E or K as this value. How can it be G? Do you understand? Because this is 2. Okay, that means 0th element of this is this, 1 element is this, 2 element is here. So you are accessing the second element of axis 1 and the fourth element. Okay, sorry, third element of axis 1 and fourth element of axis 0. So it will come here. Okay, either based on what you choose on the last axis, I may choose either E or K. Is it clear? Sandeep? Am I clear?
Yes, sir. It was Shubham.
Oh, Shubham, okay. Shubham, is it clear?
Yes, sir.
Got it, no? E only. Okay. If it was 1, suppose, then K. If you want G, this G if you are accessing, then I should have given A3 of 3 of 1 of 0, because I cannot make it 1 here because I don't know what is the value. If I make it 0 here, I make it 1 here, and this 3, then I will get G, this component. Understood?
Yes, sir.
Okay, thank you. Okay, I saw one more question there, so let me, good that you asked me. Okay, if a pixel is G, then its all face must be G or not. Okay, okay, don't confuse it with pixel now. Okay, let me tell you, what I show here, it's not about pixel, it's some dimension array. Okay, each of these elements are having something. Okay, there is no compulsion that a value in this kind of a matrix need to be the same. Okay, except that this value, okay, where is it, it is actually showing you the same one element in all 3 sides. Okay, it is like you have a F inside and it is showing up on all the faces. Okay, similarly you have a F inside, it is shown on these 2. Okay, similarly I is inside, it is shown here. Maybe if I go and look at the back, I will see the I there. Okay, similarly the back of this I will see a D here, down I will see D. So they are showing up on the face. That's why these elements are actually the cube which is inside. Okay, that cube, that value is what is h, and showing up on like a glass door. I am glass window. I am seeing it inside. Okay, imagine like that. Okay, it's a three-dimensional picture. I am showing a value. How many values are there totally? You have on one side 3 into 4, 12 values are there on this, plus 12 at the back. So 24 values are there. Don't think that there are 3 f's here. This is single f is shown as a 3f. Okay, understood, right? I hope so.
Yes, sir.
Okay, thank you. So let me, I think this is also clear, hopefully. And then, okay, now this is what I explained, that why I should do from the trailing side. Okay, I need to come from there and then start exposing, exploring whether a particular thing is proper or not. Now, before I go into some more theory, let me show you some working version so that you guys are convinced that what I am showing is fine. Okay, so let me come here. Okay, now I need to in class. So I may give you what is I have done. So in class I am, oh shit, okay, I shouldn't have taken. Okay, no problem, I'll adjust it later. Say, okay. I'll open the other file and then delete the whole thing. I don't want to show everything so that you get overwhelmed. So I'll go by one. Okay. I hope I have everything here. I did a reverse. Whatever I wrote, if I lose everything, I'm gone. Okay. Now let me take out from the class. Okay. What I am trying to tell you now, how much time I have? Okay. 45 minutes. Okay. Guys, how about additional 10 minutes also? Okay. Today. You have any class?
Yes, sir, we don't have lecture after 5.
Okay, so please, because I have explained so much, it is logically it will be good to complete everything. So let me take 15 minutes. Okay, I will take 15 more minutes, so that maybe on the lab or something we will cut down. Okay, no problem. Now what I am doing, I am having two arrays, 1D array with 4 elements, and the dimensions are same. Okay, exactly that 1D array is there. All of them are having 3 elements. So I can do the element wise multiplication because the shape is 3 comma, that's all is shape. So I can do this perform this job without any problem. Okay, no problem. Now what about this this one? So I'll quickly take this and then show you here. Okay, now what about this? What I am doing here, I am doing a scalar value and I have same matrix. I am performing a scalar multiplication, but actually I don't mean, what I mean really is, okay, let me explain what I really mean here, and what I am giving is different actually. What I really mean is element by element operation you do on this matrix. Okay, and then I am giving you another matrix of 2 comma 0 2 comma 0 2 comma 0. Now you do a multiplication between these two element wise. Then I will multiply, I want you to multiply this thing, give me the result. NumPy will give me 1 into 2, 2, 2 into 2, 4, 6. So this is what it is supposed to do. But NumPy is not very strict. Okay, it is saying, okay, even if you don't give me the same shape, if you give me a scalar value, I will assume that you are interested in doing this job. Okay, now I am going to explain something interesting thing here. Okay, it is assuming things, but is it actually advantageous to us or not? Now I will tell you the advantages. What I am giving, this is what I intend. Okay, I intend to do this. but I give these three matrix 1 comma, okay, for a short brevity I am writing 1 2 3, and then you multiply it with a 2. I am saying, when I say this, am I saving something? Really I am saving something. Suppose, okay, I need to only reserve a space for storing this 2 in my memory. I don't need to have, you know, this these three two I don't need to do. Suppose this array itself is a huge, million array. It is enough if I give one value and then I say that my intent is to multiply the same value for the same scalar value with all 1 million data. I have saved a lot of memory. Okay, one thing is I saved a lot of memory by not giving you the exact value, by giving only this. But if NumPy, while performing the job, if it is so particular that I cannot do the job unless I expand this matrix into the original matrix, I will copy 2.0 multiple times and then I will perform the job. If NumPy does it that way, then the purpose is lost. I wanted to save some memory, but this guy is now copying on multiple locations and then performing the job. Internally also, if NumPy does it, I am not going to gain anything out of this. In fact, it's going to be much laborious, because it is going to do dynamic memory allocation and then perform this job, which is not acceptable at all. So I want NumPy also not to make a multiple copies of this scalar value before performing the job. I want it to be very smart and perform the job with one copy of this. Now what is the advantage? If it does the multiplication with only one copy of the 2, as I mentioned that CPU, if it has to do any arithmetic, the value in the memory needs to come to the CPU. So this 2 would have come to the floating point register or an integer register inside. It has come to the register. Now it is going to perform it using the ALU which is inside the CPU. It doesn't have to come to the memory to pick every scalar value in the memory, 1 million entries of 2.20. It has one copy here, and then it has to anyway bring the another matrix into the register or somewhere and then perform the job with only one copy of this 2 with all the elements. Okay, so it is optimizing on the memory as well as on accessing the multiple data from the memory, because that is also optimized because it has to access only one element. So you get a better performance for two reasons. Okay, so if you mention this in one of the interviews or something, that's all, these guys will hire you immediately. Okay, so this is what is happening internally. Now you get 2 getting multiplied with all the values. Fine. Now let me do one more thing more. Okay, I am going to little bit quick I am going to be, because you will understand it. I will explain it. Don't worry that I will go running. Please stop me in case you can stop me on the mic also. Okay, don't think that you need to write there only, because I am not looking at the chat. So now what I am doing, how do I create now the 8 by 8 which I showed you in the picture. Okay, this yeah, this image. Okay, this 8 by 8 by 3, how do I build it on my NumPy? I'm sure you must be knowing it. I have to give a tuple which the shape is giving me back. At the same tuple I need to give, I let me call the tuple as a size, and then I pass the tuple which is a shape of the matrix that I want to build. Okay, the array. Okay, not a matrix. Okay, array, and I want to fill it all with ones. So I am just now making a my own image of 8 by 8 by 3 which is filled all with 1. Okay, now if I print it, I see it this way. Okay, you may wonder why is it showing it in this fashion, not the 8 by 8 what I showed you. Okay, now let me tell you what is happening. What it is showing is different from what I showed. Now what have we done? We have done now 8 by, sorry, now 8 by 8. Okay, assume that there are 8 divisions here. So 8, this is 8 by 8. I have 3 of them here. One R component, another one is G component, is like a sliced. Okay, now this is R component, G component, B component. So if I have one square here, this pixel is a 0 comma 0 comma 0. Okay, and the axis, I can say this is axis 0, axis 1, and then this axis is this axis is 2. Now each of them are different colors. That's what I am trying to construct here. Now when is it displaying? It is not showing me 8 by 8 value, another matrix 8 by 8 value, another one 8 by 8 value. But it has shown me some 8 by 3 it has shown. Now where is it coming from? You might little bit confused. Where is it coming from? Now if you look at from the top, if you look from the top, what I see here actually, I see here 8 and 3 on this side, right? This is 3. So it is 8 by 3 if I look from top. And how many entries will be there? This 8 by 3 matrix, if I print it, this is 8 numbers, 3 element. Okay, 8 by 3. This is 8 by 3. How many such 8 by 3 should be there? Because I am slicing it from the top, I should see 8 of them, right? Here below 8 are there. So either you can cut it off from the side, 8 by 8 and 3 by 3, because which is very obvious for us because we are looking at from the picture perspective. But the Python is looking at as a set of some 8 by 8 by 3 values, and then it is trying to print you from in the top. So it is showing you 8 by 3, 8 such arrays it is showing you. Okay, so what is being shown, this should be 8 number of entries should be there. RGB, each plane RGB is here. Okay, now you can say that these are all the 8 by 8 RGB plane. One slice of that is shown, another slice here, 2, 3, 4, 5, 6, 7, 8. Okay, this is how it is showing you the image in a different direction. Okay, now how is it doing it? It is doing it from the right to left. So it is taking the 3 and 8, and then 8 of them it is displaying it. That's why you see the first 3 of 8 here, another that 8 times this is going to be repeated. Okay, instead of repeating 8 by 8 3 times, it is repeating the 8 by 3 8 times. Okay, think in a different way, but number of elements in each of them is nothing but 8 into 8 into 3. That's all. Okay, I hope this is clear to you.
Hello, sir?
Yeah.
So when you say top, it is always from the 0th index, right?
Yeah.
So what we can see is when the NumPy starts printing it, first it will go to consider 3. So it will go to the 0th index and pick first 3, and then it will see there are 8 such. So it will move in the forward direction till the 8th index.
Yeah.
Then it will see there are 8 more. Then it will go down.
Yes. Yeah. It is actually printing it from here. Okay, you'll get a little bit better idea now once I do some more operations on this. Okay, just hold on, then you will exactly know what it is doing. Okay, pictorially you can have a good actually what I suggest is you try to do it yourself and then grasp it, because when I am saying it will be very hard for you to digest everything. You should digest yourself by doing it yourself. Okay, now what you are saying is correct. Let me show you some more things so that things will become clear now. Okay, now let me do one more thing. What I am doing is now the last entry refers to the 3 color planes RGB, right? This one is referring to the RGB. That's what I'm saying. Now, how can we access the red plane, which is 8 by 8? Okay, that's what I said that now in the picture I showed that it is 8 by 8 is one color R. Okay, I want to access only this 8 by 8. How do I do it? Now, red plane, NP image, I say that this is the slicing which you are aware, all the elements of that particular dimension, all the elements of this particular dimension, and 0th element of axis 3. Okay, in this our axis 1 0 2, okay, sorry, axis 2. Now it is going to display me one slice, the vertical slice of the data. Okay, now if I print it like this, I get the red plane. Okay, I hope now you'll have a clear idea how it is. Now I am making it now to give me only the this vertical slice which I done. Okay, I hope this is clear why it is doing it, because I wanted all the elements of the first two dimension and then said that I am interested in only getting the zeroth element. Then I am constructing another array, red plane. Okay, only red plane. Imagine, remember one thing, this is going to create one new entry because it is going to make a copy of that and then make a red plane from the original image, and then I am giving you, I am getting you this particular image. Okay, red. Now what if I do some scaling on top of it? Okay, I am going to show you some scaling. This we will understand how it is performing it on plane wise. Now take an example, S1, S2, S3, what I showed, scaling factor for color scaling of 3 colors. I want to color scale this red one to 2 by 2 and 3 and 4. Okay, different color things I want to multiply, which I showed you in the slide. So RGB scaling factor is 1 by 3 in size. It's a one dimension. Okay, it's an array of 1 by 3 size. I want to do a multiplication of this color scale with the image. Now, what do you expect to happen? This red plane should all be multiplied by 2. Okay, I am doing multiplication. So, it should all be multiplied by 2. Then these all should become 2 now after I perform this job on the NP image. And then all the green plane, I can access the green plane by what I do one here, I can get the green plane. Now all the green plane I should get all 3, because initially I filled it with all ones. Here all ones are there. So I am individual color plane, I am multiplying with the different values. So 4 I should get the blue. Okay, that is what I want to do. Now let me just print now what I am getting. Okay, see here. Now you can understand that all the red planes are all here 2, green are all 3 and 4. So this is what is happening when you are printing it. All of them have become 2 in here. All of them here in the green has become 3, and this are all have become 4. And when I slice it from the top, I get 2 3 4 2 3 4 2 3 4. Then again 2 3 4 2 3 4 2 3 4. So that's what I am getting 2 3 4 here. So you can imagine from the picture how what you are seeing, okay, on the screen. I hope. Any doubt, please come on the mic. Okay, it's not a disturbance, it is good for everyone. Okay, don't think that you are disturbing. Okay, now let me look at the plane, all the plane together, because in the interest of time I will do it together. Now you will have a better idea. What I am doing is I am scaling the image. Now scaled image I have already, these values are filled into the image. I have already scaled them. These are the values I have, but I want to show only only red and green and blue. As I mentioned, I need to only slice with the 1 and 2 on all the elements of 8 by 8. Then I will get the scaled, from the scaled image, I get the green plane, blue plane and red plane. Now you can imagine what you expect on this. This guy should be filled with all 2. This should be all filled with 3. This should be filled with all 4. 8 by 8 matrix you should get. So you got it. So red plane is all filled with 2. This is 3 and 4. So now you know that I am slicing it from the horizontal direction, in the horizontal direction. Okay, fine. Now this is clear. Now let us go to the next one. Okay, what do I do here? I don't know. Let me print and see. Okay, what I'm doing, shapes of, I want to apply the shape function on each of the plane. What do you expect to have? Shape is only the green plane. What is this shape? 8 by 8. So you should get 8 by 8 as a tuple, 8 comma 8 tuple for this output. Okay, always before running, just guess what you expect to happen. Before running, make a guess, irrespective of whether you understand or not. Make a guess and then run it, so that if it is different, you can understand it. If it is same, you can feel happy about it. Okay, so always do not see the result and try to reason it out. You assume something and then try to see whether what you assumed was correct or wrong. Then you will know whether you are in the right direction or not. Otherwise, you will always be behind the interpreter, or a program. Now, let us scale up different color component by different values. Now, 10, 20, 30, I want to scale up now. What do I do? Okay. How do I do? Now, I am going to take everything for you because it is not very difficult. Okay, let me just do this much. What is the time I have? Okay, I can finish it. Okay, now, what do I do? I want to scale differently. Earlier also I did differently only. Now I want to put something different value. So idea of now I want to show you when is the new array created, when it is not. Okay, how do I know? I have already told you in the Python class. ID will give you the exact ID information where exactly it is in the memory. Okay, so what I want to do is I want to check what is the red plane's ID before I perform some scaling operation, and then what do I get after that. So I want to know whether the new red plane is created or not. Please don't confuse. The variable name can be same. That doesn't mean that they are same copies. I know by now, I think you know this, because they are all just an identifiers and it is assigned a new value whenever they want. So the red plane doesn't have an identity of itself. So you may have this red plane a different in memory, and then you might get a different red plane here. Unless you check it with ID, you cannot guess it. Okay, do not make a guess. Just because I use the same name, it will be the same copy, it will be overwritten. No. Okay, so now I want to check whether really is it overwriting on the same red plane or is it creating a new one. So I can print the ID and then verify it whether I am getting a new one or not. So let me check it. Now, where is it? Red plane. See here, the ID of that is different now. That means what? When it is performing an operation, which is a division of red scale is a scalar value. I am doing a division operation on top of the red plane content. Red plane is a 8 by 8. So 8 by 8 matrix is divided by a scalar value, some 10. That means I want all this 2. I think 2 was there earlier. 2, 3, 4. 2 was there. All the 2 should be divided by 10. So I am getting 0.2 in all the entries. So when it is doing, it is also creating a new copy of the array, and then that is what is available now. The old copy is gone. That will be garbage collected on by its own. Okay, on its own. And then what I do, I am printing red plane, which I have done here. Scale down red plane, and is the scaled image which I originally had, scaled image, is it affected now? The scaled image is not affected now because it has taken a different copy. So if you are assuming that you are actually working on the image, you are wrong. So let me tell you where did we copy it from the original image. When we created the red plane, where did we create? Yeah, from the scaled image, we created a red plane. Here itself, when I say I want to only grab the 8 by 8 values of the 0th index, it has taken the 8 by 8 values and copied into new area and created a new red plane. So if you print ID of scaled image and ID of red plane here, they will be different. So scaled image is not modified, it is copied into red plane. That's why when I divide it with red plane, this is also new entry, but you can verify it whether it is the same ID or not. Maybe let us do it. Time is not there. Okay, I want you to try it out. Okay, you tell me whether what happens. Okay, I leave it to you as a home exercise. Please go and debug it further. Okay, you will have lots of understanding to make, because these are all very important things you should be clear about when you are doing any operations. Okay, now let me do the same thing on what I do. Scaled image, red scale. Okay, now I am doing something different. Okay, let me show you. Same scaled image. What I am doing is, okay, now I am taking the scaled image here, okay, and then performing a red scale operation here, and I'm doing a same dimension I have used, okay, in the sense the same arrays 3 by 3. I'm saying that you replace these values whatever I have here, okay, with the scaled values from here, okay, whatever the original scaled image I am writing it into the same scaled image here. Now I want to verify whether it is creating a new scaled image or not, or is it using the same old scaled image. So let us verify it, okay. Now I hope this is different, okay. What I did earlier was different, and I am now doing the same scaled image on both sides, and it is like a plus equal to, okay, it is equal to plus, same as plus equal to, remember, okay. Now if I do this, what do you expect to have? Is it affecting the original image or not? You can see that original image I am printing here, scaled image, it has affected it, okay. Now let us verify it whether id is also showing up same or not. Id is same, okay. That means this is like equal to writing as plus equal to, okay. What I mean by that is, when I have a plus equal to 2.0 or whatever, when I do this, the same element is accessed and it is performing the job. That's what it is same as. It is as division if I am doing, it is similar to equal to slash, maybe like this, okay. 2 dot 10.2 10.0 whatever. I'm dividing it by scaled image, and then I'm choosing only a particular element. That's why it is doing a partial operation on partial element. It is performing the job. Original image is kept, so you don't see that the 3 and 4 are not affected. Only the one plane of red plane is affected, okay. I hope this is clear. I want you to try out few things on this so that you get a clear idea on this. Now I am going to explain broadcasting. Okay, let me one by one. Okay, let me take it and then explain it and then go ahead. Okay. Oh, sorry. Okay. Now what I am doing? I take 2 by 5. That means what? 2 rows, 5 column. Now I hope you know this function. Similar to range in Python, NumPy has a range, okay. Now array range for arrays. So a range 2 comma 5, and then I am initializing it to np-a3. Okay, I'm not saying 2 by 5 is not a index. It is a range of values from 2 to 5. 5 not inclusive. That means 2, 3, 4. Okay, 3 values, and it is generating 3 values ranging from 2 to 5 and writing into some matrix A3. So A3 will have, what will it have? A3 will have, let me write it. Let us guess it, okay. So np-a3 is assigned a value which is a range, okay, 2 to 5. 5 is not inclusive, so 2 comma 3 comma 4. So by giving the values, I am deciding how many elements are to be there in the scalar, not the scalar, the one dimensional array. So I have created a value. This is how I am filling up the value with the different numbers. So NA-P3 I got it. Now what I am doing is I am creating a n dimensional array by, what is that value I am creating? I am creating a 5 by 4 by 3, or I can call it as 5, 4, 3. Okay. So I am giving a tuple with a shape. Each dimension, what is the shape? And then I want to fill that array, my n dimensional array, with all ones. I call it as 5, 4, 3. Okay, just for my clarity. Now I want you to tell me whether this addition will it accept or not. 543 with NPA3. 543 with this is also 3. So as I mentioned, it will do from the trailing direction, and it is the same numbers, and if there are no elements here, it will assume to be having 1, and then it will accept similar to our scaling. Okay, it is similar to scaling of RGB. So it should accept. Okay, it will, this plus will be done. Okay, so maybe this is different. I'm doing it differently. Another array I'm creating. So these are all one example, all fall under one category. So I will, what I get, let me explain where I am. Okay, so many things are there. 234 I created it. Okay, this is the NPA3 is getting printed, 234, and then 543 is printed like 4 comma 3 5 times. Okay, you can easily see that 4 comma 3 is printed 5 times. 4 comma 4 by 3 is printed 5 times. All ones are there, and then I am adding NA3. That means what? I am adding 234 with these values. That means one column I should all have, one is added with the 2, this one is added with the 3, and all these ones are added with the 4. So 3, 4, 5. So I will get all 3, 4, 5 now. Okay. Now I am starting another exercise, which is 24, NPA to 24. Okay. Now I want you to ask, find out whether this is acceptable or not. Now I am creating, oh sorry, what I am doing, I am creating a 2 rows 4 column. Sorry, I'm just confusing. Okay, I am creating a range of values from 2 to 4. That means 2 comma 3. That's all, because 4 is not inclusive. So 2 comma 3 I created, which is already there. Okay, don't get confused. I am getting confused. Okay, we are generating a range of values 2 comma 3, and then I want to now add that 2 comma 3 with my original array, which is that 543, which is which I got already. Now let us see whether it is possible or not. Okay, 543, this is 5, 4 and 3. I want to perform some addition, okay, with the matrix which is having only 2 elements in it. Now how do I perform this job? These are 3 are there and I have only 2. Similar to what I explained, that CX and CY, BX and BY, BZ was okay, but CX and CY was not okay, because I am having only 2 elements here. How can I perform on this? Okay, because 3 at least I should be able to match it, or I should have 1, either 1 or 3 I would have done it. Okay, but 2 I can't do, or even 4 I can't do. Okay, don't think that only 2 I cannot do, 4 I can do. Maybe suppose if I gave a 4 value, maybe use 3 of them arbitrarily and then leave out the 1. No, that is also not acceptable. It should not be anything different from the trailing dimension. Okay, so it will not allow you to do. Now what kind of error you will get? Value error you will get. The shapes are not compatible for broadcast. Okay, it's not a compatible type for broadcast. Okay, so I think I have exceeded the limit, so let me not push too much. I will stop here. I need to carry forward in the next lecture or in the lab. Do you have any questions so far? Is it clear what I explained? What I want you to do is try out few things on this different matrices, try to multiply and try to understand what exactly is happening, because that clarity is required when you want to do some image processing or any speech processing or data processing, anything you want to do. This clarity is required.